The first talk we will listen to is about abstractions. Ruby, as many as other languages, do abstract a lot, and abstraction is the bread and butter of a software developer. But sometimes you need to peel all those layers off and get to the innards, so that you can better understand, you can better explain to other people what is really happening. You can refactor and understand better the code that has been written, or that you are writing, or you are about to write. Therefore, I'm going to leave the stage to Ivan, whose talks have always been amazing. So I'm definitely looking forward to this one. Welcome, Ivan. It's super nice to see you again.
Yeah, good morning, everyone. Yeah, actually, I thought you were hosting like every Ruby Day event, because all the Ruby Days I visited, you were hosting. And by the way, like, yeah.
Nice one.
Yeah. Great.
We should show off our t-shirts. Well, as I said, it's my way to give back to the Ruby community, because I am not a particularly focused person. So every time I'm like, oh, let's try to contribute to open source, and then butterflies and my brain goes somewhere else. So at least here I have deadlines, I have to be somewhere, and I get to meet awesome people. So everything is a beautiful package that makes me consistent in my deliveries. So I'm gonna leave the stage to you. Thank you so much for being here.
Yeah, thank you. So my talk is actually pre-recorded, so I'm going to be answering stuff in chat, I guess. But yeah,
definitely. So
I leave everything to the technical stuff. How you organize.
That's a good point, because for whomever is in the chat, write your questions there. We will collect them, and I'll ask them after the talk with Ivan.
Good morning, Ruby Day. I'm Ivan Nemytchenko, and this morning we're going to make things a little bit less abstract, and we're going to be doing this by expressing Ruby OOP in pictures. Let's start. So, yeah, who's this guy? So I'm doing Ruby since 2006. I'm mostly doing freelancing and consulting these days. I used to call myself complexity fighter. Now I realize that correct word for this will be complexity organizer. I'm also a GitLab fan. I used to work for GitLab. Now I no longer work for them, but I still love GitLab. I'm the guy behind two websites, railshurts.com and painlessrails.com. And also I'm a Serbian Siberian. And this one I need to clarify a bit. So yeah, because it sounds a little bit strange. So let's clarify first where I'm from. So I'm Russian. And remember those good days when we were able to fly across the world? Imagine it's 2019 and you're traveling from some European city to some Asian city, and you know that those flights, they're really long, and probably you flew like half of your flight, and this is the point where you're like the most desperate and bored. Like you watched all the good movies, and you simply don't know what to do, and you're so bored that you start looking at this monitor where you can see the status of the flight, and you see that almost nothing is there. No, almost nothing is around, and only one small tiny dot, and there's a caption saying that you're flying over the city called Omsk. And this is the city I'm from. So this is how you might know this city. Like it is the place where you feel the most desperate while traveling from Europe to Asia or vice versa. So Omsk is in Siberia. This is the point. And yeah, and these days I live in Serbia. And yeah, Serbia is not Siberia. And before I moved to Serbia, if someone would ask me what is the difference between Syria and Serbia? I couldn't really say what is it. So those two things, they probably had like they simply meant the same thing in my mind. And yeah, and probably for you, or maybe like for some average guy who never was to any of those places, those things, they mean the same. So they mean some distant and probably pretty weird place. And today we're gonna be talking about the opposite problem, when we're talking about the same thing, but in our minds they might mean different things. So we're gonna be talking about abstractions. In programming, almost everything we operate with is abstractions. So we use abstractions which are built on top of other abstractions, and they are built on top of other abstractions. And this is why sometimes it's really hard for us to understand each other. This is one of the problems we're going to attack. Another problem is that it is really hard to see the big picture in our code when projects are huge. And if the only thing we have is the code, it's really hard to see the ideas behind those code without digging deeper into the code. There were a few attempts to attack this problem. There is this thing called CRC cards, but no one really knows about it. Someone told me that it kind of solves this problem, but no one really uses it. So I don't think it solves this problem in a good way. So, and there is also, of course, UML, but sometimes it can be useful, but no one really likes it. It's when you hear the word UML, you instantly become bored. So it can help, but we don't like it. So this was the problem statement, and now let's talk about what you can expect here. So first of all, it's gonna be fun, I promise it, and hopefully you'll become better at learning, teaching, explaining complicated concepts, and maybe techniques you learned today will help you to visualize big picture in your projects, to find architecture flow, and to track things in dynamics. We'll see. So my talk has 3 parts. The first was in the first part we're going to build a foundation. Then we're going to use this foundation to explain some advanced concepts in programming. And then we're going to experiment with those techniques in practice and see how they can be useful actually. So the whole thing actually started from the conversation at one conference in Russia, and me and several other guys who were involved in teaching junior Rubyists were talking about teaching juniors, and I asked this question. It was mostly a rhetorical question. It sounded like this: wouldn't it be great if we could just illustrate things like dependency injection in one single picture, so that everyone understands them correctly and in the same way, basically? So yeah, and I just said that I didn't mean that there could be a positive answer, but then later, several months later, I was working with my students, and I was doing a online webinar, and I was helping them with the first task related to OOP in their program. And the task sounds like this: you have to develop a smart kettle, and this kettle should boil water correctly and safely. And you don't have to write any code. You just have to come up with a set of classes and their methods. And for some students, it's really hard to start thinking in OOP way. So if the only thing they know is procedural programming, OOP might be a little bit hard. And for those who has such difficulties, I use a method called artistic soldiers method. And imagine you're captain or commander, and you have 1,000 of soldiers under your command, and you have some task to solve. And what you can do is that you can assign roles to your soldiers, and because those soldiers are very artistic, no matter what role you assign to them, they are so good at this role that if it is a role of a shovel, you can really dig holes with this guy. So yeah, and an important constraint: the only way you can interact with the soldier once you assign the role to him is that you can ask him to do something which makes sense within his role, or you can ask him something and they'll give you an answer. So, and by using this analogy, students start to understand the idea of OOP, and at some point they realize that those roles are classes, and those questions you ask and you ask soldiers, those are methods. And I love to draw pictures like this. So whenever I'm explaining something, I draw things like this, and I come up with this picture just to illustrate the idea. So how it can look like. So I started to draw those pictures of little dudes, and one of those classes or roles could be a heater. Another one can be something like temperature sensor or water sensor, something like this. And then I thought, what could be the next step after this one? What if I not only draw those dudes, but I also what could be the next step towards illustrating the idea of dependency injection. So, and then I realized that I can actually draw arms to those little dudes, and those arms will be representing methods. And yeah, so let's draw an arm. And then I took a thorough look at it and realized that, all right, it looks like it is not a simple arm, but this arm has fingers, and fingers can represent arguments. So, and it looks like it's not a simple fingers, but like tubes inside those fingers, and inside those tubes you can accept arguments. All right, let's take a next step. So it looks like our guy, who seems to be like more like a robot, he can accept accept arguments, and he can store them in the brain as instance variables, and then later he can reuse them in other methods, right? Nice. And let's try to illustrate some other things. And returning results can look like this. So arguments go inside fingers, and something happens inside, and then the result comes out. All right, nice. And then private methods. Those are arms that can't be like shaken from outside. Those methods can't be called by anyone from outside, but the guy still can use them. That's an important thing. And exception can look like this, and exception handling might look not very pleasant, but still the metaphor works. Yeah. And with this simple visual language, we can already illustrate basic anti-patterns. Basically, too many arguments, too many methods, too long methods, and too many instance variables. They are, of course, they are obvious, but when you express them visually, they become even more obvious that it is a bad thing. And this is my favorite one. So it means like too much conditional logic in methods, i.e. swollen arms. So you put so much code inside and so many conditions that internal pressure is so big that arm becomes become swollen. So, and of course there is a combination of all those problems, probably usual active record God object or something like this. Yeah, so we just build a foundation. Let's try to explain polymorphism, for example. And explaining polymorphism, and by polymorphism I mean parametric polymorphism here. With this visual language, it is almost obvious. It simply means that our classes should have, our objects should have the same number of hands and the same number of fingers. So, and this gives the same external interface, and it means that we can use those objects inside the collection in the same way. And now we can see if those guys are polymorphic or not. And now it should be obvious that they are not, because they have the same number of limbs, but guy on the right has less fingers, has fewer fingers. But their legs are polymorphic, and this illustrates another idea that sometimes we don't need fully polymorphic objects for a certain task. We can be fine with a subset of methods being polymorphic. Nice. And then let's talk about classes. And classes looks like they can be represented as a spawning platform. So there is a spawning platform, there's a lever, you trigger it, you pull the lever, and then the guy appears. So the object is instantiated. And here you put some kind of a cassette or something like this with instructions what kind of guy should be instantiated. So this is how we can represent classes. And if we take a thorough look, then we can see that those things, they actually have the same topology. And remember, classes, they're objects too. And this lever, it's actually the same as an arm, just without fingers. It could actually have fingers if our constructor had arguments. So yeah, and the topology thing is the easiest way to explain what it's. Yeah. So what I wanted to say that they have the same topology, and topology can be explained with this picture. Yeah. Come on. Yeah, here it goes. So basically a cup and the donut, they have the same topology, and yeah, I just wanted to show this nice GIF to you. And another moment is that actually, since everything is objects, things which go into our tube fingers, they are also objects as well. So it's a little bit weird, but we can't do anything. We just following the rules of this universe. So let's talk about execution flow, how it looks, how the whole thing looks inside. And it would be tempting to say that all those sections of an ARM, those are steps which are executed one by one, but we know that in most cases it's not that simple. And I would say it looks more like this, or maybe even like this, like Rube Goldberg machine, where we, as a developers, we design how all those things should be aligned, and then when arguments go inside those tube fingers, then something finally starts to happen. So we can draw something like this, and yeah, those are our arguments, and then they fall down, and then they hit some obstacles in some order, and those obstacles, they trigger some methods inside of those objects, and those methods return results, and they also fall down, and their methods then triggered, and so on and so on. And yeah, it looks a little bit crazy, but it looks like it expresses what we have pretty good. So then we have to talk about one more thing, about dependencies. And dependencies, when we talk about dependencies, we usually mean some globally available classes, and they can be reused in multiple places. So we can say that in order to use them inside some execution flow, the guy have to remember about them and put them inside the flow when it's needed. So our execution flow can look like this. So it can contain those external global those dependencies, and their methods can be also triggered. So the problem is that some of those dependencies has side effects, and it means that in order for the task to be solved, this ARM has to have holes inside it, and it is a good illustration of another idea why side effects should be isolated. And here we finally can illustrate the dependency injection. So dependency injection means that instead of remembering those dependencies and using them inside the execution flow, inside methods, we pass those dependencies as arguments and then use them. And basically we see that now we no longer have to have holes inside the arms, and those dependencies they go through as arguments. So those side effects, we can say that they are channeled. All right, so that's it. I hope that this is clear enough and you agree that this illustrates the idea of dependency injection more or less precise. And now let's this is another illustration showing that side effects are now isolated and they go through the fingers. All right, let's see how the whole thing can be used in practice and if it can be actually useful. So we've developed a visual language, and now we're going to use this visual language to illustrate a talk of Sandy Metz from 2018. And it is not that important what this talk was about. The important thing is that what Sandy does there, she solves some task, and with the new iterations, the code becomes more and more complex. And this is the first, this is how first version of the code looked like. And then with new requirements, it starts to become more complex and more complex. So let's do simple thing. Let's take this code and let's illustrate it. So this is our class in the object, and we see that we have 4 instance variables. I used legs here to represent those auto readers. This arm represents this method, which has 1 condition. And yeah, and this is a constructor with 4 arguments. All right, this is pretty straightforward. So we draw 1 picture and it represents the complexity and the nature of the code, we can say. Then the next change introduces, brings more complexity, and now the amount of complexity, we can highlight it with the red color. So we introduced 3 more methods, which are private methods. We introduced 1 more condition here. We introduced 1 more instance variables, 1 more auto reader, and 1 more argument to the constructor. Then the next step, we added 1 more condition to the private method, which was already pretty long. And the final version, yeah, so 1 more method, 1 more argument, 1 more instance variable, 1 more condition to already complex method, and 3 more private methods. Yeah, that's not what we wanted, what we want to have in our code usually. And then what Sandy does, she refactors this code, of course. And yeah, here we can see how our code was changing in dynamics. And I think that this can be actually useful to, yeah, it basically shows you the big picture. The only thing is that you have to draw those things. All right, so yeah, and here it becomes very obvious how much complexity we brought during implementing those requirements. All right, and 2 things, 2 moments where I found this idea useful. So it helps you to track what I call dynamic anti-patterns, and it looks like this. Let's say you have some classes, and then they have some methods, of course, and then you have to add 1 argument to 1 method of 1 of those classes. And then you find yourself adding the same argument to other classes in your system. And this is anti-pattern number 1, and another one, it actually has the same nature. You find yourself adding 1 condition to 1 of the methods, and then you realize that you have to add the same conditions to other methods of another classes. And this is where this idea can be really helpful. It really highlights such things instantly. All right. Then let's take a look at the resulting code which Sandy got after the refactoring. So she started to decompose the huge class into several smaller class which has simpler roles. That's the idea. So yeah, I'm not going to dive deep into the code. If you wanna dive deeper, I encourage you to watch the original Sandy's talk and probably take a look at those pictures in parallel. Then it will make more sense. But yeah, so basically this one is interesting because this is not really this is not an actual class. I mean, not an actual constructor, but it's a factory because it can return different objects of different classes. But yeah, but it still can be represented the same way because we're representing the nature of our code, not the actual classes, modules, or something like this. So not the implementation details. So we can see now that now we have that many classes, but we can see that those classes are polymorphic, those classes are polymorphic, those classes are polymorphic, and those classes are polymorphic. So we can say that they play the same role, they play the same role, and they play the same role, and they play the same role. So there are now 5 types of classes, but the actual number of classes is bigger. And this picture illustrates that if the complexity is essential to our business domain, then we can't really fight it. The only thing we can do is that we can organize it. It doesn't go anywhere. We just turn them from turn its nature from internal complexity. We are making it external. So now all the relations of those objects, they express the complexity. All right, and we're almost done. So what we've built a notation that can be used to represent complexity of our code. And yeah, of course, all models are wrong, but some are useful. And this one can be useful to draw a big picture of what you get. You can use it for modeling of complex cases. You can use it to document architectural decisions or complex places in your code. And you can use it to share knowledge between across the team. And you can use it to explain complex concepts to other developers. So that's almost it. So if you have any questions, I'll be happy to jump in and answer them. Yeah, if you're interested to learn more, you can find more about the stuff I'm interested in and I'm working on at this website, inem.at. And you can read about how I approach stuff in Rails to make it less complex and more simple on a website called painlessrails.com. That's it. Thank you. I hope you will have a good day at the conference. Bye.
Welcome back, everyone. Welcome back, everyone. Ivan, this was amazing. So,
Thank you.
I see that more or less everybody has the same question. Is there a way to generate these things, these drawings, in a way that we don't have to draw them manually because, engineers. I think that this kind of notation will make for some very interesting architectural discussions.
Yeah. So let me share the screen and show you a few more slides if it's going to work. Yeah, it is. So I actually have the same problem as you. Like, I'm a very unfocused person. So the only reason why there is a library which can actually generate those drawings is that one guy actually decided to implement it. It was my intern, and yeah, those are links where you can go and try to play with this code, and they actually can already. So the drawings are simplistic, but they can already highlight the even difference between your changes in the code. And there is even like this last link, Use Hub. This is a Rails app which you can deploy and plug into your repository, and it will comment to pull requests with pictures of those views. So yeah, go ahead and try it. There's one more thing I would like to add, is that this idea of churn faces, it was shown to me after another conference by one of the attendees, and it actually explains why the whole thing works. So the churn face idea is to use mimics of humans to represent multidimensional data. So, and here's the example of the usage where every face detail represents different thing, and after some training, like several, probably depending on the complexity of the model, you can easily grasp what is shown on the picture. Imagine if the same thing would be represented as a table with numbers. It would be much harder to grasp it. So here idea is the same. For our brains, it is more natural to grasp like human-like concepts. So this is why we quickly understand ideas behind the code when they are represented with pictures of little dudes. So yeah.
Thank you so much. I guess you will have a lot of new downloads for this tool. There is a question in the chat that is about: have you ever thought about using this visual paradigm as metrics for software development?
Good question. I had a lot of thoughts how this idea can be used. Actually, of course, we can map in this way whatever we want. We can actually collect some metrics from existing gems, like Flog, or I forgot the names, but whatever, and like, yeah, and map as those pictures. But what was the original question? So
I am gonna interpret what I'm reading. So
thank
the
you.
original intention, but from my perspective, the question is: can you use these pictures to represent the complexity of your system, and over time see how your design is getting simpler, for example, more, let's say, more elegant, if we want to put a judging label to it?
So it is essentially what it does, actually. So if you can like put on one side of the screen, you can put the code, on another side you can put this picture, and you can easily map one thing to another. The whole idea is that it is now more condensed. You don't have to dive into details every time you want to remember about architecture of this thing. And another thing that it is designed to highlight design flows. Like those are not necessarily design flows, but those are kind of signs that something can be weird here. If you see the weird picture, that it means that it could be a weird code, but it's not necessarily like this. It could be that you did that intentionally. It just gives you a hint.
Thank you. There's a second question that it's more of a how can we learn? What resources can we look at for learning and using these tools, besides attending conferences?
Not much, actually, for now. So I just encourage you to play with those repositories if you're interested in. And I would say it's still, I'm not sure if it will work good if you're gonna be, if the only thing you're gonna be doing is generating those things automatically. I think in the first play, this can be used as a tool for brains. For example, when you work on some refactoring and you are not sure how the whole thing should be shaped, or you don't like current design and you don't know what is wrong with it. I found myself this extremely useful. So I just grab a lot of paper and I start drawing those pictures, and I start understanding what is wrong with my system actually. And so I encourage you to play with it manually at the beginning, and then maybe if you're very interested, play with automated tools as well.
Absolutely. I mean, it's in its simplicity is a genius way of abstracting actually the complexity of what we design. So thank you so much for being with us, and yeah, talk to you later.
Yeah, thank you for having me. Like, everyone, have a great conference.
Bye.
Bye.